In physics class, we take a lot of measurements, and so we want to start the year by talking about taking good measurements and how the systems of measurement work. Historically, before the world was such a global place, every individual place had its own system of measurements. We're going to be doing an activity to demonstrate how inefficient this can be once you start trying to communicate those measurements with other people. And this is exactly what happened as the world became more global. It became harder to communicate with other people, and so eventually a system was proposed that would be universal and agreed upon, and it was called the System International de Units. Today we know it as the SI system. What makes the SI system so beneficial is that it is an agreed upon system where every unit has an easily reproducible standard. Today the SI system is organized such that every physical quantity has a standard that it's compared to, so that everyone in the world knows exactly what each type of measurement should be equal to. In 1971, we agreed on 7 base quantities for all other measurements, and we're going to go through each of those now. The first standard measurement is length, something that we're going to be using a lot in physics class. The metric standard for length is called the meter, which comes from the Greek word metron, which means to measure. Originally, it was a fraction of the distance between the equator and the North Pole, and then we tried to find more efficient and effective ways to reproduce this standard. So at one point, it was an actual bar that they kept under lock and key, but we've since updated it. Our current standard for the meter is based on the distance that light travels in a fraction of a second. In other words, how far a meter is based on the speed of light, something that should be universal and something that's easily reproducible. In fact, it's so reproducible that now the English system that we use in America is actually based on the meter. The second metric standard is for time. Time is going to be measured in seconds, and we're going to be doing a lot of that in physics as well. We think of time as completely related to the Earth and how the Earth spins. However, we've redefined that to be more easily reproducible, as the Earth's spin and orbit are actually not as consistent as you would think. Now, the second is redefined by the vibrations in cesium atoms. We call the devices we build out of this atomic clocks, and they measure time very, very accurately. Since the original cesium clock, we've updated it several times, and now we have a clock that can measure time accurately such that it does not get off by more than a second every 100 million years. So using atoms and their electron vibrations to measure time is incredibly accurate, consistent, and reproducible. Exactly what we want out of a measurement system. The next metric standard measurement is mass, and we use the units kilogram. It has a prefix on it because a gram is too small to be effectively used as a standard. It gets its name, gram, from the same word grav, which means gravity. A kilogram is currently defined by a physical object, and it's actually the only metric standard that is still assigned to a physical object. There's a platinum iridium cylinder that is kept in a vault under lock and key that is the official kilogram. Other countries have copies, but it is the official one. We're actually going to watch a video about the kilogram and why having a physical standard is not as great as having a sort of conceptual standard that gives some suggestions to what the future of the kilogram might be, and that's likely to change in the next few years. Mass actually has a second standard unit, which is the AMU, atomic mass unit, which is used to record mass for very small things like in the nucleus of atoms. Next is temperature, and we use the Kelvin system, which is based on absolute zero rather than being based on water. And the last three we'll use a lot less in our physics course are a mole, which we use to count things, electric current, and luminous intensity, which we use to measure brightness. Those 7 base units allow us to create an almost endless variety of derived units, and derived units are going to be a huge piece of what we do in physics. For example, one of our first chapters will take meters, which we use to measure distance, and seconds, which we use to measure time, and put them together for the unit meters per second, which we'll use to talk about speed. So we use the term SI system throughout this, but we also can call that the metric system, although there are some slight variations of it based on whether you're using meter, kilogram, and second, or centimeter, gram, second, or even the English system. In physics, we're not going to pretend that the English system doesn't exist, but we are going to do some conversions to be between English and metric, which we'll talk about soon. Whatever system of measurement we're using, the important thing to remember is that a number is meaningless without a unit behind it. No naked numbers. So make sure any measurement you use this entire year, you put a unit with it. Something else we'll be using this year as we take a lot of measurements is scientific notation based on powers of 10. And so you are going to want to remember how to use scientific notation, brush up on that, and how to use significant figures to give answers that only have the amount of accuracy as your actual measurement had. There are a bunch of rules for significant digits that you'll want to review. Feel free to pause here and read through these. But a key takeaway is that zeros are sometimes not significant, but basically if you are actually taking a measurement with a measuring device, you're going to be writing down digits and they're going to be significant. And those digits then are going to limit how many digits you can have in any calculations you do with those numbers. Speaking of calculations, there are certain rules for calculating with significant digits. And one of the big ones I want to point out right now is when you multiply or divide in this class, you need to round your answer off to whichever the lesser number of significant digits in your original number was. So when you have a number with only 3 significant digits, like in this example, your final answer should only have 3 significant digits, whether you write it in normal notation or scientific notation. We're also going to be doing a lot of unit conversions in this class, whether it's going between metric and English or even just converting within the metric or within the English system. You're going to need conversion factors. These will typically be given to you, and there's also a huge list of conversion factors in your textbook. And then you want to arrange the conversion factors such that the units you want to end up with are on the top and the ones you want to get rid of are on the bottom. Then you simplify, the units you're getting rid of will cancel, and you'll be left with a final answer. Feel free to pause this slide and look at the instructions more, but you will need to be able to do unit conversions throughout the year. One thing to be aware of when you're doing unit conversions is that converting between units does not change your significant digits. So whatever your original number was, however many digits it has is how many digits you should get when you are done doing the conversion. The final thing I want to mention about measuring is that you need to know some of the common metric prefixes and how to convert between them, and as well as what their scientific notation is for each of those units. For example, kilo is equal to 10 to the third. It's equal to 1,000. So if you're not familiar with those, make sure you brush them up. You're going to get practice with all of these measurement skills I've mentioned in this during your homework for this chapter. Good luck.